Have you ever wondered what really happens behind the scenes when you click a button on a website? Today, we are following a single request through the entire architecture of a modern web application, so you can understand exactly what happens, from DNS resolution to backend databases. By the end of this video, you will have a deeper appreciation for all the moving parts that make your favorite apps run smoothly. When a user types example.com into their browser, the DNS acts as the internet's phone book, translating the domain into an IP address. This IP address could point to a load balancer or a AWS CloudFront distribution, depending on the architecture. Quick DNS resolution is crucial because it helps reduce initial load times, ensuring users can access your site quickly. So if you are using AWS Route 53, it helps you direct the user to the closest available server, ensuring fast and efficient routing. Next up is the Content Delivery Network or CDN. Services like AWS CloudFront cache static assets, images, videos, and CSS files at edge locations closer to your users. This helps reduce latency and speeds up load times, especially for users spread out across different regions. And in today's world where even a 1-second delay can lead to drop-offs, speed is everything. Not only does CloudFront improve speed, but it also helps reduce cost by offloading requests from your main server, especially when handling global traffic. Before the request reaches your backend services, it passes through Web Application Firewall or WAF. A WAF is your application's first line of defense. Imagine someone trying to hack into your system using SQL injection or cross-site scripting attacks. WAF stops those attacks in their tracks by filtering out malicious traffic before it even hits your backend services. After passing through WAF, the request reaches Nginx, which serves as a reverse proxy. It routes traffic, handles SSL termination, and caches dynamic content. Now, while Nginx offers fine-grained control, but services like CloudFront or ALB can handle many of these tasks, making Nginx an optional component in certain architectures. However, when you need more control over routing, caching, or SSL termination, Nginx becomes a valuable addition. Now, the load balancer ensures availability by distributing incoming traffic across multiple backend servers. With NLB or Network Load Balancer, you get low latency, high throughput handling for applications that need extreme performance, like gaming or financial services. On the other hand, an ALB or Application Load Balancer gives you advanced routing capabilities, ideal for web apps and microservices, where requests need to be routed based on specific paths or hostnames. Both Network Load Balancer and Application Load Balancer operate at different layers of OSI models. Previously, I have made a video on the OSI and TCP layer, breaking down and explaining each of these layers with practical examples. NLB operates at the transport layer, which is the layer 4 of the OSI model. This means it forwards traffic based on the IP address and port number, without inspecting the content of the request, for example, HTTP headers or paths. It is designed to handle protocols like TCP or Transmission Control Protocol and UDP, which stands for User Datagram Protocol, which makes it suitable for high-performance, low-latency applications handling very large amounts of traffic with millions of requests per second, while maintaining very low latency. This makes it ideal for real-time applications such as gaming or services where speed and throughput are critical. ALB operates at the application layer, which is the layer 7 of the OSI model, which means it can inspect the content of HTTP or HTTPS request, making it suitable for web application, REST APIs, or microservices architecture. It can route traffic based on attributes like request paths, for example, routing based on specific API paths like API users or API products. Or it can also route traffic based on attributes such as hostname. For example, a request to example.com/API can be routed to a backend API service, or a request to example.com/static can be routed to a different service that handles static content. The API gateway acts like a traffic cop, validating requests, ensuring the user is authorized, and enforcing rate limits. Rate limiting and throttling prevent any single client from overwhelming your system, keeping everything running smoothly. After this, the request is routed to the right backend service, whether that's an EC2 instance, a AWS Lambda function, or a microservice running in Kubernetes. Once the API gateway does its job, it's up to the backend services to handle the heavy lifting. Now, in microservices architecture, each service is dedicated to a specific function, allowing teams to work independently, scale services more easily, and make updates without impacting the entire system. For instance, One service might handle user authentication while another process payments, with each service able to scale or update separately, all while interacting with databases like PostgreSQL or DynamoDB. Speaking of databases, they are the heart of your application, where your persistent data is stored. For distributed applications that need to scale dynamically, a NoSQL database like DynamoDB works best due to its flexibility and ability to handle unstructured data. Meanwhile, for applications with structured relational data, an SQL database like PostgreSQL is often the best choice. For asynchronous tasks, requests might be passed to message queue like Kafka or SQS, which handles tasks that don't need immediate processing, such as email notification or background jobs. In addition to handling requests, your application likely uses additional layers like authentication, using OAuth 2.0 or OpenID Connect, IAM, or JWT, basically to verify users. Caching can be used to speed up responses and logging for tracking system health. Services like Redis or Memcached can cache frequently requested data, reducing the load on backend services. Monitoring tools like Prometheus or AWS CloudWatch ensure your system is running smoothly by tracking metrics and identifying issues before they escalate. Now that your backend services and additional components have done their job, it's time for the response to make its way back to the user. This journey is just as important as the request itself, and it follows a similar path back through the system. So the process response is sent back to the API gateway, which may apply additional formatting or transformations before routing it to the client. The load balancer efficiently routes the response back to the user's original request, balancing any outgoing traffic if necessary. And if any static content was part of the response, such as images or cache data, it can be served directly from a CDN edge location to minimize latency, ensuring a quicker response. Finally, the response reaches the user's browser or mobile app, displaying the requested data, completing the full request response cycle. In a well-designed system, this entire journey from the user's request to the final response happens in milliseconds, ensuring fast, reliable performance. From DNS resolution to the database and everything in between, every layer plays a crucial role in delivering a smooth, fast experience to users. Understanding both the request and response lifecycle gives you a solid foundation for designing resilient, scalable systems. Let me know in the comments if you'd like me to dive deeper into any of these topics, and don't forget to like, subscribe, and hit the notification bell for more deep dives into cloud architecture and system design.